Example 2. We want to find the points on the graph of y equals 4 minus x squared that are closest to the point 0, 3. So I'm just going to draw a picture. You don't have to, but I want to draw a picture so you understand what's going on. What does 4 minus x squared look like? Well, here's 4 minus x squared does create a parabola that opens downward. Here's the point 0, 3. Right here would be the point 0, 3. And the idea is we want to find wherever the point is on this function, the function being y equals 4 minus x squared, we want to find which point is closest on the graph is closest to this point. Now, because of the symmetry of this, my guess is if we find one point, we're actually going to be finding 2 points because it's equal distance on the right side of the y-axis as it is on the left side of the y-axis. Heck, there might be 1 point if it's just that point right there, but we'll see. How are we going to do this? Well, notice what are we trying to do? We're trying to find the point that is closest. In other words, we're trying to minimize distance. So let's think about the distance. What is the distance formula? Well, if you remember the distance formula, it's the square root of the change in x, x2 minus x1 squared, plus the change in y, y2 minus y1 squared. So that's how you find the distance between 2 points, and this is what we want to minimize. We are fixed on one of our points, though. We know that one of the points has to be 0, 3, and we don't know what the other point is. So let me go ahead and plug in the point 0, 3 here. I would have d equals the square root of, well, instead of x2, I'm just going to put x minus my x value is 0 squared, plus instead of y2, I'm just going to put y minus the y value would be 3 squared. Let's go ahead and clean this up again. This would be distance equals, well, this would be x squared. I'll go ahead and FOIL out y minus 3 squared. If I FOIL out y minus 3 squared, I'd have y squared. Then I'd have minus 6y plus 9. Remember, you get that by FOILing y minus 3 times y minus 3. FOIL that out. So this is the function that I want to minimize. The problem with this is this has 2 variables. We can't do this with 2 variables, so we need to get this in terms of 1 variable. So I either need to know x in terms of y or y in terms of x. Well, the nice thing is if I look at this, I actually have what y is. Y is 4 minus x squared, so we already know what y is in terms of x. So what I can do is get this function into 1 variable. This would be the square root of x squared plus, well, let's think of what this would be. It would be 4 minus x squared squared minus 6 times 4 minus x squared plus 9. It's ugly, it's nasty, but we could go ahead and clean this up. Let's do the distance equals the square root of, well, we would have x squared. Let's see here, 4 minus x quantity squared. If I FOILed it out, 4 minus x squared times 4 minus x squared, I'd have a 16. I'd have a minus 8x squared. Then I'd have a plus x to the 4th. That's FOILing out the 4 minus x squared quantity squared. Now let's distribute that negative 6 through. Negative 6 times 4 would be minus 24. Negative 6 times a negative x squared would be plus 6x squared. And then I have a plus 9. Let's get all this put together and see what we get. Putting it in descending order, looks like I have the square root of x to the 4th. That gives me that term. I have an x squared minus 8x squared plus 6x squared. Looks to me like we'd have a minus x squared out of that. That gets rid of my x squared terms. I have a positive 16 minus 24 is negative 8 plus 9 would be a plus 1. So now I have my distance formula in terms of 1 variable where I can minimize this. This is what I want to minimize. Of course, if I'm minimizing this, I'm going to be taking the derivative of it. So if I'm taking the derivative of this, I'm going to be using the chain rule on this problem and look at it as a power rule of 1/2. So let's go ahead and try to minimize it now. Let's find the derivative of this function. The derivative of this function using that chain rule, you drop the power down, so that would be 1/2. Keep the exact same thing, x to the 4th minus x squared plus 1. Power minus 1 would be 1/2 minus 1 is negative 1/2. Times the derivative of the inside using that chain rule. The derivative of the inside would be 4x cubed minus 2x plus 0. So it's 4x cubed minus 2x. Let's go ahead and clean this up because we are going to be setting this equal to 0 or undefined. Because it's raised to the negative 1/2 power, I am going to throw that into the denominator, and 1/2 is a square root. So on top it looks like I have 4x cubed minus 2x. On bottom it looks like I have a 2 times the square root of x to the 4th minus x squared plus 1. Okay, what do I do at this point in time? Well, let's see if we could simplify anything. I do notice on top, it looks like on top I can pull out a factor of 2x. If I pull out a 2x, let's see what we would have left. It would be 2x squared minus 1 all over 2 times the square root of x to the 4th minus x squared plus 1. The 2's could simplify. Looks like I'd be equaling to the simplest form of the derivative that I can find, or that I see, is x times 2x squared minus 1 all over the square root of x to the 4th minus x squared plus 1. A nasty looking function, but that is the derivative. So what do we care about? We care about where's the derivative equal to 0 and where's the derivative undefined. Okay, remember a fraction is equal to 0 when the numerator equals 0, so let's solve that now. This would give me x equals 0. This would give me 2x squared minus 1 equals 0, so that would be 2x squared equals 1. X squared equals 1/2. Take the square root of both sides. I'd have x equals plus or minus the square root of 1/2. If you plug that into your calculator as the square root of 1 over the square root of 2, it'll rationalize the denominator for you, and you end up with root 2 over 2. So we have three critical values. We have 0, we have negative root 2 over 2, and positive root 2 over 2. Those are my three critical values. I also need to check when is this thing undefined. Well, remember, a function's undefined only when, fraction is undefined only when the denominator is equal to 0. So for the denominator equal to 0, we would have to have this function right here equal to 0. And if you look at this right here, because it's all even powers, x to the 4th, x squared, and 1, and we're adding 1, this can never equal to 0. So we don't need to worry. This is always a positive number. We don't need to worry about when is it undefined. It's never undefined. So we have our critical values at this point. We have options. We can either do the first derivative test or the second derivative test to prove that this is the minimum. This is a nasty looking derivative, and anytime it's a nasty looking derivative, I'm going to go ahead and do the first derivative test instead. So I'm thinking about that number line. I'm plotting those points, negative root 2 over 2, 0, root 2 over 2. I'm thinking about those intervals, and I'm thinking about the derivative function. Remember, at these points, the derivative was equal to 0 at all three of those points. I'm going to choose some test points. I'm going to throw it into the factored form of the derivative, 2x squared minus 1, all over the square root of x to the 4th minus x squared plus 1. Again, though, we know that that denominator is always positive, so we don't have to worry about that. I'll put that over a positive number each time. Okay, let's continue. I need a number that's to the left of negative root 2 over 2. How about negative 10? I need a number between negative root 2 over 2 and 0. I don't know. How about negative 0.1? That'll work. I need a number to the right of 0 in between that's smaller than root 2 over 2. How about 0.1? And I need a number bigger than root 2 over 2. How about 10? Let's see what we get. Just the sign of them for each of them. So if I plugged in negative 10, I would have a negative times a positive over a positive, which is negative. If I plugged in negative 0.1, I'd have a negative times a negative over a positive, which is positive. If I plugged in 0.1, I'd have a positive times a negative over a positive, which is negative. And if I plugged in 10, I'd have a positive times a positive over a positive, which is positive. So I have negative, positive, negative, positive. First derivative test says anytime I go from decreasing to increasing, I have a minimum. Anytime I go from increasing to decreasing, I have a maximum. And again, decreasing to increasing would be a minimum. This problem wanted the points where it was minimized. So I know my x values, which does make sense because it does, if you go back to the picture, makes me think of the symmetry of the property of 4 minus x squared. I now know the x values of those 2 points that minimize them. I know the x value is negative root 2 over 2, and I know the x value here is root 2 over 2. So the question is, what then is the y value? Well, how do we find the y value? Just plug it in. Y equals 4 minus, well, it'd be root 2 over 2 squared, or negative root 2 over 2 squared, which truly doesn't matter. Let's see what we get. Using my calculator, I'm getting 7/2, or 3.5, depending on if you have it written as a fraction or a decimal, and truly I don't care which one. So it seems like these are our 2 points that minimize the distance from the point 0, 3 on the graph of 4 minus x squared. A very difficult problem, but please make sure you rewatch this video to figure it out. I have negative root 2 over 2, 7/2, and positive root 2 over 2, 7/2 is the answer to this problem. Okay, just a quick review. What the heck did we do? Started off with the distance formula, plugged in the point 0, 3, simplified it, substituted in for y, simplified it again, found the derivative, simplified it, set it equal to 0, looked where it was undefined, found our critical values, tested those critical values using the first derivative test to prove that they are indeed minimums, found the y values, gave us the points on the graph. I know I just talked through it real quick, but that was a very long, very difficult problem. Let's go ahead and take a look at this next one. All right, let's take a look at this next problem. It says a rectangle page will contain 54 square inches of print. That's the gray area there, the shaded area. Let me go in and shade this for you. Right here, this is the one that has to be 54 square inches. They've given the dimensions x and y according to the picture for us. Okay, it says the margins at the top and bottom of the page are 1.5 inches. So here's the margin on the top of the page, and here's the margin on the bottom of the page. Each one of those has to be 1.5 inches. So if we're considering this picture right here, the total length of this page, or height of this page, whatever you want to call it, that would have to be x plus 1.5 plus 1.5. In other words, x plus 3 inches. 1.5 plus 1.5 is 3. Okay. It says the margins on the side are 1 inch wide. So what are we talking about here? We're talking about this area right here. This blue area has to be 1 inch, and this blue area here has to be 1 inch. So if we consider the width of this page right here, we would have y plus 1 plus 1, which would be y plus 2. Okay. So if I'm looking at the area of the page, or well, let's finish the problem. It says, what dimension should the page be to minimize the amount of paper used? Minimizing the amount of paper used would be minimizing the area of the shape. So let's think about the area. Area is always length times width. Well, again, we have x plus 3 would be the length, and y plus 2 would be the width. What's our issue with that? Again, it's in terms of 2 variables, so that won't work. So what we need to do then is think about, is there any other given information? Well, the other given information says it has 54 square inches of print. So the printing area is just this interior rectangle right here. That interior rectangle is length x, width y. So it's x times y. And I know that has to be 54 inches. So we can use this equation with the given information to solve for either of the variables. I'll solve for y because typically that's what we're used to doing. So I'll divide both sides by x, and I'll have y equals 54 over x. Again, it doesn't matter which one of those variables I solve for. It's totally up to you. But what do I do at this point in time? So what I want to do is I want to come back and I want to look at this. This y equals 54x. I'm going to plug into my area equation in terms of 2 variables to get my area equation in terms of 1 variable. So let's do that now. I'd have the area equals, well, I'd have x plus 3 times, instead of y, now I'm going to put my 54 over x plus 2. All right, so what do I do now? Let's go ahead and distribute everything out and see what we get. I would have 54 over x times x. I'm foiling it out. Plus 2x. Plus 3 times 54 over x. Plus 6. Let's go ahead and simplify that. Looks like in the first term my x's are going to simplify. In the next term I could do 3 times 54. 3 times 54 is 162. So let's see what we end up having here. So I have 54 plus 2x plus 162 over x plus 6. Again, combining like terms, let's write it. It doesn't really matter what order we write it in. So I'm going to have the area is 2x plus 162. I'm going to write it as x to the negative 1 so I can use the power rule and I'm finding the derivative. And then I'm also going to put the plus 60. So that's my area in terms of one variable. Let's go ahead and minimize or maximize that by finding the derivative. The derivative of 2x is 2. The derivative of 162x to the negative 1 would be minus 162x to the negative 2. And the derivative of 60 is 0. I'm going to clean this up a little bit. This would be a prime equals 2 minus 162 over x squared. Again, we want to find this equal to 0 or undefined. When is this undefined? It's undefined whenever the bottom, or x squared equals 0. In other words, x equals 0. But if we look at that, x being 0 would mean the length of the page is 0. That makes no sense to us whatsoever, so let's not consider that case. Let's go ahead and solve the other one. I'd have 2 equals 162 over x squared by adding that 162 over x squared to both sides. Multiply both sides by x squared. I'd have 2x squared equals 162. Divide both sides by 2. I'd have x squared equals 81. Take the square root of both sides. I'd have x equals plus or minus 9. Again, negative doesn't make any sense here. So x equals 9 is the only critical value that I need to consider. It's the only critical value that I need to consider. I need to prove that this is a maximum or a minimum. Again, I could use the first derivative test or the second derivative test. That first derivative is not too bad, so I'm going to go ahead and use the second derivative test to do this. If I use the second derivative test, again, I'm going to be looking at the derivative as 2 minus 162x to the negative 2 is how I'm going to be looking at this. The derivative of 2 is 0. The derivative of negative 162x to the negative 2 would be negative 162 times negative 2, which is 324. Then it would be x to the negative 3. Which is the same thing as 324 over x cubed. I go ahead and I plug in 9. When I plug in 9, it would be 324 over 9 cubed, which is a positive number. Because it's a positive number, the second derivative positive means it's concave up. Because it's concave up and it's that critical value, it's that point right there, that means it is indeed a minimum. So I've proven that when x equals 9, I have a minimum. But let's go back and let's reread the question and make sure we're answering what they actually wanted. It said, what should the dimensions of the page be to minimize the paper used? Well, x, let me go back and highlight this for you. X equals 9. X is just this little part right here. So what dimension should the entire page be? Well, let's think about it. The length of it had to be x plus 3. So x plus 3 in this case, would be 9 plus 3, which is 12 inches. So 12 inches should be the length of it. I look at the width of it. The width of it was y plus 2, but we already know what y is. Y is 54 over x. So y would have to be 54 over 9. So y is 6. And then we had to add 1 inch onto each side. So when I look at y plus 2, I'm really looking at 6 plus 2, which would be 8 inches. So what are the dimensions of the page? The dimensions of the page are 8 inches by 12 inches. It's very close to the standard height and width of a page to minimize the area. So if you think about it, why did we do what we did when we created pages? A standard sheet of paper is 8.5 by 11. Well, the reason we chose 8.5 by 11 wasn't by choice. 8.5 by 11 was the minimum amount of paper you could use when you were trying to have a certain area of print. It wasn't 54 square inches, but whatever it was. So again, to quickly review the problem, we started off with the area of this rectangle. We realized by the labeling of it that the area was x plus 3 times y plus 2. This had two variables, so we had to look at a different equation. That was the area of the inside rectangle. X times y had to be 54. Solve for one variable in terms of the other. Plugged it into the original area equation. Got that in terms of one variable. Simplified it down. Found its derivative. Found its critical values. Made sure that it was a minimum. And then interpreted the answer. Notice x equals 9 was our critical value, which was proved as a minimum, had absolutely nothing to do with the answer in this problem. You had to do a lot more work to actually find the dimensions of the page. So don't think that the critical value is necessarily the answer to the problem. Always make sure you interpret the answer to the question.